All right, so in Chapter 2, we're going to look at logic and reasoning, and we're going to start with the mathematical process. So in this first problem here, the warm-up, it asks us to look and continue the pattern. So in this first one, we've got 3, -4, 5, 6. So it looks like it's increasing and alternating. So I'm going to go 7, and then -8, 9, and then if we kept going, -10, 11, and so on. In the next one, we've got 7, 0, 14, 0, 21. So it looks like it alternates with a 0. Then the other number appears to be going up by 7, so 28. And then a 0, so the next one would take us up to 35. In the next one, we've got 2, 5, so it's up by 3. 5, 10, up by 5. Then we've got up by 7, up by 9. So the next move I'd go up by 11, so 37. The next move I'd go up by 13, which would take us to 50. And the next move I'd go up by 15, which would take us to 65. In this last one, we've got 1, 1, 2, 3, 5. All right, this is a little bit trickier one, but if I take the 1 and 2 and add it, I get 2. If I take the 1 and 2 and add it, I get 3. So 1 plus 1 is 2. First two numbers added gives me the third number. The next two numbers added give me the 3. 2 and 3 give me 5. 3 and 5 give me 8. 8 and 5 give me 13. 8 and 13 would give me 21. All right, we could keep progressing up as we go through. Now, this last pattern, it looks like each of them alternate dot or no dot. So in this next one, I'm definitely going to have a dot. I've got 3 sides in the first picture, 4 sides in the second, 5 sides, 6 sides. So I would anticipate 7 sides in this one. All right, so as I go through, I need to add one more side to that. All right, and that was my best attempt at a heptagon right there. All right, so we've got 7 sides, 1, 2, 3, 4, 5, 6, and 7. All right, and it should be regular. My hand drawing is not the best. Now, what we used to complete each of those problems in the warm-up was really inductive reasoning. And in inductive reasoning, basically you use evidence to come up with a generalization. All right, or a hypothesis, something you're basically going to make a prediction, all right, a conjecture about what would happen. And the conjecture is typically going to be framed in a conditional way, where it's if I see this, then I see this. So inductive reasoning goes from specific events, and it draws a general conclusion out of it. Now, this can be right. It could also be wrong. We're basically basing things off evidence, so we're making a prediction about the future. The conjecture is basically the prediction, so it's the generalized finding that was based on inductive reasoning. All right, and then a conditional statement is basically an if-then statement, is how we're going to think about it. It's if this happens, then this is going to happen. All right, so when we look at inductive reasoning, it's basically a generalized finding based on evidence. All right, and that generalized finding we call a conjecture, and often we word it in an if-then statement, which is a conditional statement. Now, if I jump to this first problem here, it says make a conjecture using the following example. So they've got 3 plus 5, which is 8, 7 plus 11, which is 18, 13 plus 1, which is 14, 9 plus 3, which is 12, 37 plus 5, which is 42, and 121 plus 21, which is 142. So if I was looking at those numbers, one conjecture I might draw is that if you add 2 odd numbers, then the resulting sum is even. All right, so if I add any two odd numbers, we're going to make the prediction that then it's going to result in an even sum. Now, another example of making a conjecture uses the following examples. All right, I have noticed that students with the last names A through L have been in my classroom every Wednesday since August 31st. All right, so this is another example where I'm basically drawing a conclusion based on the evidence I've seen before. All right. So based on that evidence, the conjecture I might make is if it's Wednesday, then all students with last name A through L are in my classroom. All right, so now when we look at this, there might be counterexamples that we can come up with. So a counterexample is a reason or example that shows a conditional statement is false. So for this particular example, a counterexample might be a student whose last name is A through L, but isn't enrolled in my class at all. Or another example could be a student that happens to be sick on a given Wednesday. So it may be Wednesday, their last name may begin with an A, but they're not in my classroom because they're sick that day. Now, that's the downfall of inductive reasoning, is that our predictions aren't always right. And we haven't proved with certainty that that has to be the case. We've come up with a good argument, but it's not a certain argument. Certain arguments is where deductive reasoning comes into play. And deductive reasoning, we use general principles we know are true to show something must be true. All right, so we're going to use general principles, things that we know have to be true, and we're going to use that to prove that something else has to be true as well. So there's a certain certainty with deductive reasoning that you don't get with inductive reasoning. So in the earlier example, we looked at adding two odd numbers. So 3 and 5 was 8. 7 and 11 was 18, 13 and 1 was 14. All right, so the conjecture we made was if you add two odd integers, then the sum is an even integer. All right, but we came about this from inductive reasoning because we went through tons of examples and came up with that. So we're going to start and look, is there a counterexample? So you can pick any two odd numbers you want. I'm going to pick 123 and 2,212. Oop, that's an even one, so I'm going to have to change that. So let's make that a 5 there for that last number. All right, if it'll let me erase there. All right, there we go. So let's make that a 5. If I add those together, I get 2, 3, 3, 8, which is even. All right, so my random check was true, and if I could keep trying this, I don't think we could come up with a counterexample. So what we might do at this point is we might try and prove it. All right, so if I look at an odd number, every odd number is an even number plus 1. All right, and even numbers are divisible by 2. So I might consider one of them as 2n plus 1. All right, that's definitely going to give me an odd number. Then I might consider another one that's 2a plus 1. All right, the a and the n are different, so we know they're different odd numbers. So let's say n was 1, a was 2, we'd be looking at 3 and 5. So now I'm going to look at adding those together, 2n plus 1 plus 2a plus 1. That's 2n plus 2a plus 2. Now from there I can factor a 2 out, and I've got n plus a plus 1. So since this is 2 times something, we know it's even. All right, and we've actually proved at this point that for sure if I take two odd numbers, so odd number 1 and odd number 2, and I add them together, right, I must get an even answer. All right. Now, when we prove something's true, all right, the next thing we typically do is we look and say, well, does it work the other way? All right. So biconditional, all right, is a conditional statement that works both ways. All right. So if and only if is an example. All right. So we've said if I add two odd integers, then the sum is even. All right, so if it's biconditional, then it would have to be if the sum is even, then I added two odd numbers. All right, so biconditional would have to satisfy both of these. Unfortunately, this one right here is false, because if I have two numbers, a plus b, that equals an even, like 32, that could have been a was 30 and b was 2, which aren't odd numbers at all. All right, so this counterexample doesn't work, so the statement wouldn't be biconditional. We could prove it in one direction, but not both. All right, so now if I look at the definition of perpendicular, a lot of times biconditionals are used for that. So two lines are perpendicular if and only if, and a lot of times we shorthand that IFF, all right, if and only if they intersect to form a right angle. All right, because if two lines intersect and form a right angle, we know they're perpendicular. If they're perpendicular, we know they intersect to form a right angle. All right, and we've actually already checked to see if I could make that earlier conjunction into a biconditional, and we could not. It was false. All right, now in summary from today, basically what we're looking at is the mathematical process. Real math, when it's actually done in practice, almost always follows this pattern right here. All right, we use inductive reasoning to identify a pattern. We make a conjecture in the form of a conditional statement. So we make a prediction based on what we see in the pattern. All right. Once we have that, we test that conjecture to see if we can find any counterexamples. So we do a lot of samples, a lot of examples, and see if any of them don't follow the conjecture that we came up with. All right. If we can't locate any counterexamples, then we move into the deductive reasoning. We say, you know what, I can't find any counterexamples, so I'm going to try and prove this definitively. All right, and once we do that, we determine if the conditional statement can be written as a true biconditional. So if we can prove it in one direction, then we're going to go in and we're going to actually flip it around and try and prove it in the other direction. Because there are values in conditional statements that are if-then, which a lot of times we write as P implies Q. All right, but biconditionals are even more powerful. So if we can write them as P if and only if Q, then we get more power and we can do more things with that conjecture and that proved statement that now becomes a theorem. All right, so that was today's notes. I hope that was helpful. That should get you through tonight's homework. Have a great day. Bye.